Okay, hello and welcome everyone. In this video, I'm going to walk through some more consumer theory videos or consumer theory exercises. So I'll start with number 27, 28, I'll do 29, I'll do 30, and I'll do 31, and 30, and 32. Yeah, I'll go up to 32. So let me pause this that you can, put this that you can pause and take a look. 24, these preferences. 28, Cobb Douglas. 29, another Cobb Douglas with a twist. 30 is like a Cobb Douglas where we're looking at some comparative statics. And 31, which is actually just a standard perfect complements, but it's dressed up in a way that looks kind of scary. So sorry about that. And then I'll start this at 32 for my next video. All right, so 27, Anne has preferences described by utility is going to be twice times the natural log of x plus 3y. Anne's income is 14. Price of good x is 2. Price of good y is 3. What are Anne's demands for x and y? All right, we got to find the marginal rate of substitution. So the MUX, marginal utility of x, is going to be 2 times 1 over x. So 2 over x. The marginal utility of y is just 3. So 2 over x divided by 3 is going to be 2 over x divided by 3, that's small. 2 over x divided by 3, that's what this is. All right. And then this 2/3 is coming from the price of good x and price of good y is 3. So those things cancel off nicely. So the demand for good x is just going to be 1. Now we could find the demand for y using the budget constraint. X is equal to 1. The budget constraint is going to be 14 is equal to 2x plus 3y. 14 is equal to 2 plus 3y, so y is equal to 4, right? 14 minus 2, so 12 divided by 3 is y. All right. Now Anne has Cobb-Douglas utility. Here's Anne's income. Here's the price of good x, the price of good y. Solve for Anne's demands for x and y. Well, I think I did this. Yeah, I did do it right here. We can do this with a Lagrangian. So this is my objective. This is my constraint. I'll take the partial with respect to x. This is going to be 1/2, reduce the power by 1. So 1/2 x to the minus 1/2. This y to the half comes along for the ride. The partial here is just going to be minus lambda px. Take the partial with respect to y. It's going to look just like this, but now it's going to be a minus 1/2. Okay. And then here's my partial with respect to lambda. It's just the constraint. Then I'm going to set, this is right here, this is marginal utility of x divided by marginal utility of y. This is price ratios. But you could solve for lambda, and then you could manipulate to get MRS is y over x. Price ratio is px over py. My expenditure on good x is pxx, and the expenditure on good y is pyy. I actually so I left out some steps there. I kind of go through those steps in some of my other Cobb-Douglas videos if you want to see that a little bit more carefully. Then I'm going to substitute this into the budget constraint. Remember, I like to substitute for as much as I can. So rather than solving this for x and substituting for x, I'm just going to substitute directly for my expenditure on in this case, y. So I got pxx plus pyy, or pxx plus pxx. And then sure enough, my Cobb-Douglas demands are going to be x star is going to be m over 2px, and y star is going to be m over 2py. All right, then we're asked what happens for x and y if the prices are 2 for both. So I'm just going to use these demands. My income was 100. 100 divided by 4 is 25, right? Then the last thing was, suppose there is a tax. Suppose the price change. So in part B, I was saying, suppose there's a price change. Price of good 1 went to price of good x went from 1 to 2. Fine. We never calculated it when the price ratio is 1/2. We only calculated the generic version, and so that actually basically was irrelevant for part B. I'll show you that. Let me just go up here. So that was this right here. So the prices of x and y were originally px is equal to 1, py is equal to 2. Suppose the price of good x increases by $1, so now the price of good x is 2. After the price increase, what bundle of x and y will Anne now choose? That's why we just skipped right here to price of good x is 2, price of good y is 2. Good. Then it says, suppose this price increase of $1 is due to a tax. Fine. We're not doing like the full supply and demand tax example. We're just saying there's a $1 increase and it happened because of a tax, and the consumer's paying $1 more because of a tax. And so how much revenue does the government earn? Well, it's going to be those 25 units times the $1 that's taxed. So revenue is 25. 29, Anne consumes only B and D each week with $100 income. So beer is $1, donuts were 50 cents. Preferences are going to be U of BD is going to be equal to B times the quantity D minus little d, where D is the quantity of donuts that Bob consumes. All right, so how does Bob's donut consumption influence Ann's utility function? So we want to differentiate with respect to capital D. So if we do that, let's see, the derivative here of D is just 1 times B, so it's just going to be minus B, right? Wait. No, we're taking the partial. Sorry. The D was. Here I'm trying to do things quickly. Ann's consumption of donuts was capital D, and then Bob's consumption of donuts was little d. So it's going to be this minus 1 is the partial. So the partial I'm going to take is du d little d. So that's where this minus b is coming from. All right, so this means Ann's utility function decreases as Bob consumes more donuts. Other things equal, apparently Ann does not like to see Bob consume donuts. Holding Bob's consumption fixed, compute Ann's optimal consumption of donuts and beer. Good. So you do this like a standard Cobb-Douglas. Marginal utility of beer was going to be d minus d, right? Because that was this. Take the partial. That's going to be this. Partial with respect to D is now it's going to be that capital B. Good. So you'll have D minus D over B. The price ratio was 1 over 1/2 or is equal to 2. So the tangency condition is just going to be D minus D is equal to 2B. Substitute into the budget constraint cleverly. What did I substitute for? I've got B plus 1/2 D is equal to 100. So B plus 1/2 times 2B plus D, right? Solve this for D and then replace. So 2B plus little d, right? Multiply this half. Actually, I need parentheses here because I need that half to get distributed, don't I? I think I did. When I did it, yeah. Did I have the word? I thought I could have sworn I did this. Yeah, I did. I meant to do this more carefully. All right. So here, sorry. I wrote these out in advance and then I didn't get a chance to make the video. So now I'm coming back and doing it and I forgot the places where I was trying to add stuff. So anyway, so here is that substitution. Good. Wait, the substitution I was doing a second ago was this one. We're substituting into the budget constraint. And so anyway, so you're going to get your demands for D star is going to be 100 plus 1/2 D, and B star is going to be 50 minus 1/4 D. Okay. Anyway, so that's what these were doing. How's Bob's consumption of donuts affect Ann's optimal bundle? Let's take the partial with respect to Bob's consumption. So now that we've got Ann's demands, let's take the partial with respect to little d. So Ann's demands was right here. Take the partial. It's going to be this 1/2 for this one. And then the partial, this one's going to be minus 1/4. So Ann, as Bob consumes more donuts, Ann consumes more donuts. That's this. Ann's consumption of donuts is increasing in Bob's consumption of donuts because the derivative of Ann's donut demand was positive with respect to Bob's donut demand. Ann consumes less beer, so Ann's beer consumption is going to be given by this partial, which is minus 1/4. Okay, that's what that's doing. All right, and then the next one was the pollution masks one. Ann lives in a city with air pollution. Pollution's a bad, able to avoid. So here's the utility function. This is Q1 minus P. Capital P is pollution squared, and then Q2 squared. Q1 is the time spent wearing a mask. P is the amount of pollution. It's composite of other goods. Big P should be the amount of pollution. Ann decides how much to wear and how many masks to purchase, or how much other goods to purchase. So the price of a mask is P1. Assume initially Q1 star is bigger than P. Okay, derive Ann's demands for masks. So I can't remember I don't think I did that. Yeah, so let's take the partial with respect to this thing, with respect to Q1. So 2Q1 minus the quantity, 2 times the quantity, Q1 minus P, reduce the power by 1. This part comes along for the ride, that's this. And then the partial down here, marginal utility of good 2, is going to be 2 times this stuff. Okay. Price ratio is just P1 over P2. Simplifying this down, this is a lot of canceling. You're going to get Q2 over Q1 minus P is equal to P1 over P2. From this, I realize, oh, if I move this to this side, this to that side, Q2, P2 is just the expenditure on good 2. So that's the substitution I'm going to make into my budget constraint, which is my expenditure on good 2 plus my expenditure on good 1. So that becomes this. And then simplifying, my demand for masks is just y plus P1 times the amount of pollution divided by 2P2, or 2P1. That was this right here, so I did that work. All right, part B. How does the quantity of pollution affect the demand for masks? Well, here was my demand for masks, so let's take the partial and sign it with respect to pollution. So dq1 dp is going to be 1/2, because this is going to be a 1 for the numerator. This is going to be the 2 from, we can think of this as like 1/2 times this stuff. All right. So she buys more masks when the pollution increases. How does her income influence the quantity of masks? So let's sign this with respect to income. Same thing. It's going to be increasing with respect to income increases. So we're going to have take the derivative with respect to y, and so that's also going to be positive. What condition must hold for the amount of masks to exceed the amount of pollution? I would just start with this statement, then replace the demand. So the demand was this stuff right here. Okay, that's my left-hand side, and then leave this on the right-hand side, and then just simplify down. Move this to the other side. Good. So I've got y plus P1P. It's bigger than 2P1P. And then move this to the other side. So I have y is bigger than P1P, and then y has to be bigger than P1 is bigger than P. So that's where that came from. All right. Consider a consumer of the following preferences. This is just perfect complements. It looks scary. This is just maximize this utility statement. Maximize utility written like this. Solve for the consumer demands, and then find the indirect utility function. So observe, this is similar to just regular perfect complements. So the consumer is going to set. We're going to replace this comma with an equal sign to give us the line through the origin that goes through the corners. So it's going to be alpha is equal to, or x is equal to alpha x2. Plug that into the budget constraint, and then, so that's this right here, P1 x1 plus P2 x2, replacing P1 alpha x1, or x2 for x1, right? That's that substitution. And then simplifying, I get x2. I'm factoring out an x2. I have P1a plus P2, and then x2 is just going to be this stuff divided by that. I've made so many videos today in the last 2 hours, so all right. So then the indirect utility function, you plug these into the original utility, right? So you plug your Marshallian demands, your optimal selections, into the original objective to get your indirect utility function. That's what this is doing. So I'm going to take this, I'm going to plug this in here. I'm going to take this and plug it in here. That alpha comes along for the ride. And so I see my indirect utility is whichever is the smaller of this side and that side, or it's just alpha over the quantity alpha P1 plus P2. All right, so I'm going to stop here. I'm not going to take a break. I'm going to finish these videos, and then I'm going to go outside and cross-country ski, because it snowed a lot, and I bought these skis, and it never snows in Grand Rapids, and so it snows like 4 days a week. There's snow on the ground. There's deep snow for like probably 3 weeks out of the year, when I thought there was going to be a lot of snow, and there's not, and so I'm going to use my skis.